Okay, last section for everybody, BC included, is 7.6, which is about logistic models. And these are good. You know how I told you guys, like the last section we did 7.5, I told you guys, oh, you know what grows exponentially is populations grow exponentially, as if they grow like this. And that's kind of true up to a point, but like in real life, things can't just keep growing and growing and growing and growing forever, especially populations like on Earth, because they like resources run out and stuff like that, which is what this little part says. So eventually you have to reach a point where it's like you can't have any more people than this, or people are gonna die, I guess. So it does grow exponentially for a while, populations do, but then eventually they gotta level off, and that's how logistics functions. That's what this part is saying. Carrying. Okay, that place where like you can't have any more people than this asymptote is what's called the carrying capacity, is what it says here. In this case, the growth rate is not only proportional. Oh, okay. So what this part is saying is that the way that you set up this differential equation, so watch this. A differential equation for an exponential model says the more you have of something, the more it can continue to grow. In other words, as population grows, so does the rate of change. But for logistic equation, this is true up to a point, but as you get closer and closer to this carrying capacity, your growth rate has to slow down. So not only does it depend on the population present, but how far that population is from the carrying capacity. So that would be, what do they call it down here? Carrying capacity L is what they call it. So difference between the population and the carrying capacity. That is a logistic equation. And if you tuned out, tune back in for this part, because this is kind of all you need to know from this section in terms of what I'm going to ask you and the AP test is going to ask you, is what does a logistic equation, differential equation look like? It's just this. You don't even got to know what the solved version looks like. You just have to know this. Well, that and kind of one more thing, and that's basically it. So watch this. A good example. It says, imagine a rumor spreads through a school of 2,000 students. Well, the more people that hear the rumor, then the more people that they can tell. So that's going to grow more and more as more people hear it. But then as a bunch of people hear it, then there's less people to tell. So once you hit a certain point, the rumor is going to start slowing down as it spreads. Like as the 2,000 students all get close to hearing it, there's fewer people to tell. So that would be a logistic equation with a carrying capacity of 2,000. That's what this little part is saying. The rate at which the rumor spreads is proportional of both the students who have heard it and the students who have not heard it. The curve is called a logistic curve, and this type of growth is called logistic growth. Here's an example. One thing that I have to point out from here, this says what I was saying up there, is that this is how logistic equations look. But the big thing to point out from here is that look at how the curve is growing the fastest right around here, which is always going to be halfway to the carrying capacity. So at 1,000, that's when the rumor would be spreading the fastest. Exclamation mark, exclamation mark, exclamation mark. So if you just want to hear the summary and be done, basically all you need to know is this is what logistic equations, differential equations look like, and you have to know that it grows the fastest when the population is halfway to the carrying capacity. All right, cool. One more little caveat is that sometimes they like to write it with a 1 here instead of the carrying capacity. Like they factor out that L out of the whole thing. You'll see that in a second, but just be prepared for it. Could either look like this or they could factor the L out and it'll look like that. Cool. All right, let's see some examples. Okay, look at it. Says the rate at which the flu spreads through a community is modeled by that logistic differential equation where T is in day. It says how many people had the flu at the time when it was growing the fastest. So if I don't say nothing, you already know the answer? What is it? Yeah, there you go. Fastest spread would be halfway to the carrying capacity. The carrying capacity is 3,000, so therefore how many people had the flu when it was spreading the fastest? Half of 3,000, so 1,500. Solid. And then part B says, what was the rate of change of the spread of the flu at that time? So hopefully you know, put that 1,500 in for the P, and that'll be the rate of change. Okay, that's the rate of change, but I think I calculated this before. Yeah, I did. And that is 2,250. 2,250 people per day. Cool. All right. I think I just put one more on here because for real, that's all you're going to get asked on the AP test. It says the rate of growth of a population of bears in a newly established wildlife preserve is modeled by that differential equation where T is measured in years. It says, what is the carrying capacity for bears in this wildlife preserve? Okay. So again, this is why I was warning you before, because if you're like, oh, I know carrying capacity, it's always right here. Oh, shoot, it's one bear, question mark. Then you would be wrong. It's not that. You guys know what it should be? What is 100? Yeah, it's the 100 that was factored out from this. So if you wanted to make this look like the other ones, then you would have to like multiply the 100 back into the parentheses and take it from this 0.008. See what I'm saying? So if I were to distribute times 100 into here, I would have to take the 100 out of this to give it to you. So what I mean is, here's what it would look like if it was written like the other one. But that's so many zeros and so ugly that you could just look at this 100 like standard. But either way, whether you rewrite it or not, a carrying capacity would be the 100 that Sam talked about. D says, what's the bear population when it's growing the fastest? You guys would all say what? Nice. And then the rate of change of the population when it's growing the fastest, plug that 50 in. I calculated this one. Yes, I did, and that's 0.2 bears a year. Yes.
I remember last year on the AP test, we couldn't, there was like some policy about doing like half of like a like physical thing, where it's like a living person, you can't do like half of like you can't do 0.5 of this person because that's not like a thing that exists. is there a rule like that on the calculus? or
Not
is
that
it-
I know of, and if there, Lindsay's asking about how last year you couldn't do, like, if the thing was a population, you would have to round this down or up to like the whole bear per year. But I don't know of anything like that on the AP test, but if they wanted that, they would say it's like round to the, yeah.
Okay.
All right, and then like I said, that's the last thing I put on here because the next are just like examples
Whole person.
that I took straight from the old AP test. And I recommend that you listen, because this is what you're not going to expect this from Mr. Cordero. I recommend that you don't do these right now, so that you can come back later and see if you remember how to do them. Because this is kind of all the practice problems I have is these ones from the AP test. So I kind of recommend you just chill, do something else, and then come back in a few days and see if you remember how logistic equations work, so that you don't do them all in one day and then never think about them again. All right, nice, y'all, good job. That's all from me.